Hello everyone, my name is Silinya Mahawong. I am a master degree student in Energy Engineering program, Faculty of Engineering, Konkan University in Thailand. Today I would like to present my work, Optimization of Low Temperature Torrefaction for Rice Store Upgrading. The outline of my presentation are introduction, methodology, results, and conclusion as seen on the slide. So let's start with introduction. Increasing in population and technology have resulted in high energy demand. Renewable energy resources have thus touched down much attention as alternative energy resources. Biomasses are agricultural waste left in the field and sometimes are burned before the next crops. These biomasses can be utilized as alternative fuel in biomass power plants. Rice is one of promising biomass, particularly in Thailand. It is considered as waste left in the field after harvesting periods and mostly burned, causing smoky and PM 2.5 problem in the windy city. Thus, dry store utilization is of interest. Moreover, as it has low fuel characteristics, it is also required to improve its quality for the ease of storing and efficiency combustion. Therefore, upgrading rice store by a thermochemical process called torrefaction is of interest. It is a process using a temperature range of 200 to 300 degrees Celsius under air absence environment for removing moisture content and light volatile matter from the rice store. Nevertheless, as under low temperature, the main production is commonly in solid phase and called torrefied biomass. Torrefied biomass has low moisture content and low oxygen per carbon and hydrogen per carbon ratio, resulting in higher heating value. Moreover, torrefied biomass can improve cleanability and resistance of biological degradation. And this slide is about methodology. Rice straw was prepared by cutting into 2 to 5 centimeter pieces. Then higher heating value was examined as illustrated in Table 1. The instrument that used in the experiment is a frequent reactor. It is made of stainless steel having 50 mm outside diameter and 1000 mm length. The temperature were measured and controlled by K-type thermocouple and proportional integral derivative temperature controller. 15 grams of rice straw were fed into the reactor. After that, feeding nitrogen gas as 500 mm per minute at the beginning until a set temperature was reached. Then the flow rate was reduced to 200 mm per minute. During the reaction time, the experiments were planned by central composite design between 200 to 300 degrees Celsius, reaction time 25.7 to 54.3 minutes. The heating rate was set at 5 degrees Celsius per minute. Data correction includes mass, heating value, and electrical energy for calculation of energy yield and specific energy consumption. The temperature and reaction time are shown in Table 2. Each run was repeated 3 times and the results were evaluated. Value and energy densification ratio can be calculated from equation 1 and 2 as shown in this slide. The torrefaction was optimized by using energy yield and specific energy consumption during the process as determined by equation 3 and 4. For optimization, energy yield and specific energy consumption are considered as the main factor to obtain and optimize temperature and time for the best rice stall torrefaction. As you seen in figure 6, the 25 rice stall and some selected conditions were illustrated. It was obviously seen the difference of appearance. The color of rice stall became darker when using higher temperature and longer time. Table 3 shows the material higher heating value, energy densification ratio, energy yield, electrical energy, and specific energy consumption for the 13 lines designed by CCD. It was found that material were ranged from 35.98% to 86.24%. It was reported that torrefaction gave biomass valorization because of moisture content, moisture reduction and decomposition of hemicellulose. An increase in temperature and time resulted in lower material and higher heating value. As seen in the table, the energy densification ratio was risen from 111.5 to 147.1% when the temperature was increased from 200 to 300 degrees Celsius for 40 minutes reaction time. This indicated that the quality of rice stall was improved by 11.5% to 47.1%. The energy yield of torrefied rice stall ranged from 52.91 to 96.16%. It was obvious that higher temperature would result in lower energy yield. The decrease can be explained by the thermal decomposition of rice stall. In optimization, not only energy yield but also the specific energy consumption was considered. This was because the specific energy consumption indicated the energy used during the process per a unit of torrefied product, which was particular for economic point of view. It can be said that optimized condition was obtained at high energy and low specific energy consumption. This led to the conclusion that there were two effective optimized conditions which gave high energy yield and low specific energy consumption. Firstly, at 200 degrees Celsius, 14 minutes, and secondly, at 215 degrees Celsius, 30 minutes. As shown in figure 7, it can be said that high temperature and long reaction time resulted in high energy consumption, but less material. This gave high specific energy consumption, which is not suggested that the high heating value and energy densification ratio were high. It's worth noting that not only high heating value but also material must be considered for torrefaction optimization. In this work, rice stall was upgraded by torrefaction. Low temperature torrefaction was forecast while reaction time was varied. The temperature and time were ranged at 200 to 300 degrees Celsius and 25.7 to 54.3 minutes, respectively. Based on the results, it was finally concluded that the highest energy yield of 96.16% and lowest specific energy consumption of 23.73 watt-hour per gram were achieved at 200 degrees Celsius and 14 minutes, while the second best energy yield and specific energy consumption by 94.06% and 25.5 watt-hour per gram, respectively, were obtained at 215 degrees Celsius, 30 minutes. Thus, the two conditions were suggested for rice stock upgrading via torrefaction. The research team would like to thank the Department of Mechanical Engineering, Faculty of Engineering, and Center of Alternative Energy Research and Development, Konkan University, for supporting our work. All authors are as follows: Ms. Linya Kyaw Mahavong, Assistant Professor Dr. Walin Lampai Sethanabut, and Professor Dr. Thanakorn Bong Wachanasathian. Thank you for your attention.